Hey, so this is Joe, and this is the second part of the sixth chapter of Stewart's calculus. We're going to be talking about exponential growth and decay. So exponential growth and decay happens when we have some value that the rate of change of which is proportional to the amount present. So this applies to a lot of things, like population growth, for example. Very simple population growth, like the culture, like bacteria cultures. The rate of growth or decay of that population is proportional to the population that's there at a given time times the relative growth rate, which is a constant. Now, it also applies to temperatures. So when Newton's law of cooling, which we're going to talk about later, we're going to do a problem with that, where you have something, the temperature of which is changing in some medium with the constant temperature, and the rate at which that changes is proportional to the temperature. So you've still got the same differential equation. Differential equation because it is an equation with a derivative in it. And it also applies to things like radioactive decay, where the amount of radioactivity in something is decreasing, and the rate at which it decreases is proportional to the amount present. So why is this, do we have growth and decay here? Well, and how does that happen? Well, it happens based on the relative growth rate. If that k, the relative growth rate, is greater than 0, then we've got growth. And that makes sense because the derivative is positive. It's changing in a positive way. And if the relative growth rate is less than 0, we've got decay. And that makes sense because you've got a negative derivative then. And so, but then how does this become exponential? Because this looks not exponential right here. Well, we're going to solve this differential equation. And this is the only kind of differential equation we're going to solve, the first degree separable differential equation, where we can basically separate this derivative and then integrate. And that's the only kind of differential equation we're going to be able to do in this course. But it's a really helpful one in terms of explaining lots of different kind of exponential growth and decay. So I'm going to show you how we separate this, and if you encounter a AP free response question that involves anything where the rate of change is proportional to the amount present, you have to show all of these steps in this problem. You can't just jump to the conclusion at the end, even though that's a helpful way to think of it, or think of the problem. Okay, so we've got dy dt equals ky, and we're trying to find an expression for y, just an expression for y in terms of t, to kind of map out how this thing is growing, and not just map out its derivative. So we're going to need to integrate somewhere in here. But we can separate this derivative by multiplying the dt over to this side. So we've got dy equals ky dt, and we can't integrate this because we've got y on this side of the equation. We need to isolate the y's and the t's. So we can have dy over y equals k dt. And now that we've separated like this, we can integrate both sides. This is something we know how to integrate. That's a natural log. So we'll get the natural log, the absolute value of y, equals, we integrate this, we just add a t, kt plus c. And generally we'd have a c over on this side, but then we could always, subtract it over from this c, and so this c includes both of the constants that could come out of either side. So now we use our properties of logarithms. This y is an exponent. This over here is an exponent. So y is equal to e to the kt plus c. And now this is a step that I can prove with a lot of algebra, but you don't need to in the AP, so just kind of take my word for this holding, and it's a good thing to memorize. We've got y equals c e to the kt. And this c right here, the way it works out, can also be expressed as y0 e to the kt as some initial amount of y, be it population, radiation, or temperature, that's present once this exponential growth or decay starts to happen. So this is kind of this is where calculus stops being involved in this problem. And generally, if you're using like a on a multiple choice problem, just start off with this equation. But if you are doing a free response problem, you need to do all the steps to get to this point, and then start plugging in values depending on what equation or what type of problem you're going to be doing. And so we're going to start, in the rest of this video, we're just going to be doing some practice problems involving kind of this concept. Alright, so we're going to be doing number 2 from page 451 in your book. This is just a pretty basic exponential growth problem. So it's going to be growth, but it's population growth. So common inhabitant of the human intestines is this bacterium, and the cell of this bacterium divides into 2 cells every 20 minutes. So it divides into 2 cells. That means every 20 minutes the population present gets cut in half. And the initial population of the culture, so that C in that equation that we just saw, is going to be 60 cells. So we need to find the relative growth rate, which is the K, and find an expression for the number of cells after 2 hours. Alright, so let's go back over to the white screen. I'll bring all this information over, and we'll solve this problem. Alright, so I'm not going to do the whole derivation from the natural growth, the law of natural growth. I'm just going to start off from right here to show you how you kind of continue on. So we've got the population is equal to the initial population times e to the relative growth rate times time. And so we know that the population doubles every 20 minutes, and we have 60 cells to start off with. So p at time equals 20 is going to be twice the initial, so that's 120, which is going to be equal to the initial 60 times e to the 20, that's going to be time, 20 minutes, k. And so we need to find the relative growth rate, we need to find k. So we can divide 60 over, so we'll get 20 is equal to e to the 20k, and we can take the natural log of both sides, so that will be natural log of 20 is equal to the natural log of this, and since this is in the exponent, this can come out as a coefficient. So we get 20k natural log of e, and that's 1, so we can kind of ignore that. So now we'll get natural log of 20, oh sorry, this is not 20, that's a 2. The natural log of 2, my bad, 120 divided by 60 is 2. The natural log of 2 over 20 is equal to k. And so that was the A part of this problem. Now let's go on to do the B part, which is find an expression for the population. So we plug this k back in to our general expression here. So we've got P of t is equal to the initial population, which is 60, times e to the ln of 2 over 20 times t. Now remember, we have that property of e, where if you have e to the natural log of something, you just take the argument. Well, that means we need to get all these coefficients up into the argument, and we do that by making them an exponent of the argument, based on the property of logarithms. So we'll get 60 e to the natural log of 2 to the t over 20, and so then this natural log and that e go away, and we get 60 times 2 to the t over 20, and that is our exponential growth formula for that population. And again, that's why it's called exponential growth, because you've always got it grows in an exponential manner. So now let's go on to our next problem, or next type of problem, which is Newton's law of cooling. So what Newton's law of cooling tells us is that the temperature, or the rate of change of the temperature of an object, so either it's cooling or it's heating, is proportional to the difference between that object's temperature and it's the temperature of its surrounding medium, which for this purpose we're going to consider to be a constant, as well as the relative growth rate. So we can do it. This can be set up as a separable differential equation like the last one, and again, for free response problems you need to do this entire derivation, but for multiple choice you can kind of skip straight to an equation that comes out of this at the end. So let's separate this. We're going to isolate the t's and the big t's and the little t's. So we get dt over t minus ts equals k dt, and to get rid of those little differentials we'll integrate. But wait, we don't really know how to integrate this. But remember that Ts is a constant, so it looks like we can do a u substitution. So let's call u T minus T sub s. Then du is equal to dt. Yes, that's good. It looks like we can substitute stuff in there, so we'll get du over u. We know how to integrate that. That's a natural logarithm. When we integrate this, we'll get kt plus c. Integrate that, we'll get the natural log of u, but let's substitute in for u, and it's the absolute value, remember? Big T minus T sub s equal to kt plus c, and then we'll use our property of logarithms, and we get T minus T sub s is equal to, and then we're going to do the fancy c thing, c e kt, we'll bring the ts over to that side, and then we'll get t as a function of little t. The temperature of the object as a function of little t is equal to c e to the kt plus the temperature of the surrounding medium. So that, again, is kind of where the calculus stops. We get that function. Now let's actually do a problem where we go on, plug in values, solve for other values, but we'll just use this. We won't redo the entire derivation. But you, on free response problems, do need to do this entire derivation each time. Alright, so we're going to be doing number 14 on page 453 in your book. So in a murder investigation, the temperature of the corpse was 32.5 degrees Celsius at 1:30, 30.3 an hour later. So we know already that the relative growth rate is going to be negative, because this is going to be exponential decay. And we're using Newton's law of cooling. Temperature is proportional to the difference between the temperature of the object, in this case the body, and the surrounding medium, in this case the room. So the normal body temperature is 37. So that means that the person died before 1:30, because there was some time when the temperature of the corpse dropped from 37 to 32.5. And the temperature of the surroundings, that's 20 degrees, and we're going to make that constant. So what we need to figure out is when the murder took place. So remember, in our Newton's cooling formula, that C that's the initial temperature of the body, and we can make that whatever we want. We'll just end up using negative time, which is fine. So I propose that you begin using 32.5 as the initial, because you know what time that happened at, and you know what the temperature was at some other interval of time, so you'll be able to figure out the relative growth rate. That's what I would recommend. And then when you're figuring out at what time the corpse was 37, you'll get a negative time, but all you'll have to do then is just subtract that from 1:30, and you'll be able to figure out the exact time of death. So let's go over to the white screen and do that. Alright, so now we've got all our information, and the first thing we need to solve in order to figure out when the person died is the relative growth rate. So in order to do that, we need to plug in a value for t at a certain time, the initial time, and the temperature of the medium, the surrounding medium, and we have all that information. So we know that after 1 hour, between when it was 32.5 degrees and 30.3 degrees, the body temperature changed by that much. So temperature is going to be 30.3, and that's T after 1 hour. And because 1 hour previous the temperature was 32.5, that's going to be our initial temperature, even though its initial temperature was actually 37. But for the sake of ease in this equation, we're going to call it 32.5 times e to the k 1 plus 20. So we're going to subtract 20 over, and that will get 10.3, and we can divide 32.5, so that'll be 32.5 is equal to e to the k. And now we can use properties of logarithms and take the ln of both sides, and that will be natural log of 10.3 over 32.5 is equal to k. And so now we have our natural growth rate. And we can go back up here then and plug it in for the equation. So t is going to be equal to 32.5 e to the, and remember, it's a negative, it's exponential decay, so this has to be negative. Even though it doesn't come out of the equation, we've got to put the negative in there. ln 10.3 over 32.5 t plus 20. And we need to figure out when the body temperature is 37 degrees. So we'll plug a 37 in there and solve for t. And the t will end up being a negative time, but that's good because it's time before 1:30. So actually we can subtract we can subtract 20 from 37 and we're going to get 17, and we can divide the 32.5 directly, 0.5, and that's going to be equal to e to the negative natural log of 10.3, that is a 10, over 32.5 t. And remember, we can just make this t an exponent, or I should say this negative t an exponent of that fraction, and then we'll get rid of the natural log. So let's do that. And so, we get rid of the natural log, but we keep the fraction. So it'll be 10.3 times 32.5 to the negative t is equal to 17 over 32.5, and we can take the natural log of both sides, and then this negative t will come out as a coefficient, and that will give us the natural log of 17 over 32.5 over the natural log of 10.3 over 32.5 equal to, we can bring the negative over here, and that's going to be equal to time. So we do have that negative over here, so we're looking good. There are ways that we could solve this by ourselves, but I recommend that you just plug this into your calculator. If you got a problem like this, it would be on the calculator section. And so time, once we do that, the time is equal to negative 0.5639 hours. And so the question asks us at exactly what time did the person die. So this would, if the patient was 32.5 degrees at 1:30, this is a little over half an hour, so they probably died at like 12:57 or something. But that is the basic gist of how to do this kind of Newton's law of cooling problem. So now we're going to move on to talk about one more kind of exponential growth and decay problem, and that is continuously compounded interest. Alright, so this is the general equation for compounded interest. We've got some sum of money, or some initial sum of money invested or borrowed, times 1 plus the rate of interest, so that's going to be in a percentage, and here you're going to write it as a decimal, over the number of times in a given time period you compound the interest. So sometimes you could compound interest annually, in which case that n would be 1, or you could compound it semi-annually, in which case it would be 2, so on and so forth, and then this n, that's the same. So that equals the total sum of money that you're going to have afterwards. So if you borrow $1,000 at a interest rate of 0.6 and it's compounded, or not 0.6, that's really high, 0.06, which is 6%, and that's compounded annually, you'd get 1,000 times 1.06 to the 1, because it's 1 year, 1 time, and then this A of t would be the total amount you would owe after interest. Now, people in finance said, well, what happens if we make this n approach infinity, continuously compound the interest? It doesn't stop compounding. What would happen then? Well, let's see what happens. So that we would get, and your book describes this in more depth, but I'm just going to kind of jump straight to the conclusion. You'd get A of O times the limit as n approaches infinity of 1 plus 1 over n to the n times RT. And now, does this limit look familiar? This limit actually converges at E. This is equal to E, and that's another reason why E is so important, because it's the number that allows bankers to continuously compound interest, and it makes people investing. It makes investors seem more appealed, and it also does better for people who lend out money. So our continuously compounded interest formula is A of t times A of O e to the RT. Now this looks pretty familiar. This is a step that we eventually get to in our once we solve the differential equation of the law of natural growth. That means that when we continually compound interest, the rate at which A is changing is proportional to the amount of A that's there. So again, when you're probably going to end up needing to solve that entire differential equation if you have a problem like this on the AP free response. But for now, we're just going to solve one problem already knowing and using this. So here we go. Alright, so this problem is not in your book, but let's say you borrow $1,000 at 6% interest, and it's compounded continuously. How much will you owe in 3 years? So we've got our handy continuously compounded interest formula. So we find A of 3, because you want to know what that's going to be in 3 years. The initial sum of money is 1,000. E to the R is going to be 6%, so we write that out as a fraction, 0.06, and you put a 3 in there. That will get us 1,000 times e to the 0.18, and then we can plug that in our calculator, and we will get 1,197.21 dollars, and that's how much you would owe in 3 years at that rate. So that's it for exponential growth and decay. In this video, stay tuned for the rest of Chapter 6. We're going to be getting to that really fun, really helpful way of solving limits later. So stay tuned.